So this section is about taking a non-linear curve and using logarithms to transform it into some kind of straight line. It's a bit tricky, but quite interesting. Okay, so first case is when you have a curve y equals ax to the n. Now that could be some curve like, it could be something like this, it could be something like this. Okay, so it's a non-linear curve. Okay, so we can use logarithms to transform it or code it into a straight line equation. So the procedure is you take the equation, you log both sides, and then you use the log rules. Okay, here you got a times x to the n. So by the first log rule, that can be separated into log a plus log x to the n. Then by the third log rule, if you've got something to a power, that can be written as n log x. Okay, so altogether, you get log y equals log a plus n log x. Okay, so I've taken log base 10. So when I use log, I'm talking about log base 10. So they've written it in this form over here. They've rearranged it. Log y. They've put this term first. Okay, so you can identify it as a straight line equation in disguise because if you look at it. So these are the two variables. Okay, the a and the n are just constants. So you can think of it as a straight line graph of log y, the dependent variable, against the independent variable, log x. The y-intercept will be this term over here. So that is the y-intercept. Okay. And the gradient is just equal to n. Okay. So what I've done so far, I've taken a non-linear curve, y equals ax to the n. Using logs, I've transformed it into the equation of a straight line. Okay, but the graph you plot is not x against y, it will be log y against log x. That would produce a straight line equation with y-intercept log a. And the gradient of that line will be equal to the constant n. Talk to me. Any questions? I need to do an example to make it a bit clearer though. So, okay, on the example, they've given you data about populations of various cities. So this is page 329. You've got the population of 5 different cities: Birmingham, Leeds, Glasgow, Sheffield, and Bradford. You also have the ranking of the city. Okay, so if you look at the table, ranking and population, you'll see that basically as the population decreases, the rank is increasing. Okay, so you can see maybe as the population decreases, so that's the first observation. As the population decreases, so it starts off at 1 million, goes down to 480,000. As P decreases, the ranking of the city, so maybe that's to do with how important the city is, the rank increases. Okay, so they've excluded London as an outlier. Okay, so what I've done initially is plot the data, population against rank. Okay, so you can see from that data that the red points are close to some kind of curve. Can you see that? That's the first observation, that the plotted data forms some kind of a curve. So the idea is to find the equation of that curve. Okay, so first of all, what I've done is you can actually work out the equation of that curve by using software. So I've used this website, mycurvefit.com, and I've inputted the data, and they've given me this equation for free. So according to the website, they've calculated it as P equals this number. So that number is approximately 1.6 million. And this power of x, so this power of x is r, so this power of r is minus 0.68 approximately. Okay, so you can use software to calculate the equation of a curve that fits the data as best as possible. Okay, so this website has done the calculations here. Okay, but you can do the same kind of process. You can work out the same kind of equation using logarithms. So you can do your own estimation of the equation of this curve by using logarithms. So this is what I'm going to show you next. So in the question, the first thing you need to do is to draw a table of, okay, so this is what you need to do. Draw a table of log R against log P, first of all. Okay, so what they've done is they've gone through all the values of R, and they've worked out the log values. Log 2, log 3, log 4, log 6, etc. They've gone through all the population values, and they've done the log of each value. So log of 1 million is 6, log of 730,000, 5.86. Okay, that's what they've done so far. Okay, so the theory says that, okay, so if you're working with the equation P equals A R to the n, so you're trying to find A and N. So according to what I've done so far, if you log both sides, use the log rules, you can separate it as log A plus n log R. Okay, so remember, log P is the dependent variable, so this is on the y-axis. I'm going to rearrange this to write, think of it as gradient, and this is the independent variable. So log R is on the x-axis, so this is the y-axis, this is the x-axis, and this constant log A, this will be the C term, this will be the y-intercept. Okay, so using logs, if you log the equation, you end up with a straight line equation. Okay, so that's why they've asked you to calculate log R and log P. Okay, so once you've done those calculations, you plot the graph of log R against log P. So they've plotted log R, independent variable, on the x-axis. They've plotted log P, the dependent variable, on the y-axis. And if you plot it, you get a straight line. Okay, this is what you expect anyway. So if the original data is close to a curve, then the log of the curve will give you a straight line. Okay, so the next step then is to work out the equation of this line, and hence the equation of the curve. So this is where you can use your graph. So I guess the first observation would be the y-intercept. Okay, so the y-intercept is this number here. Okay, so if you read it off as carefully as possible, that value seems to be approximately 6.2. Okay, so from the curve, from the straight line, y-intercept is 6.2. So that has to be equal to this bit over here. This term is the y-intercept. Okay, so that tells you that log A, remember this is all base 10. Then to work out A, you just reverse the logs, 10 to the power of 6.2. So if you work that out, that will be approximately 1,600,000. That will be approximately, if you do it on a calculator, 1.6 times 10 to the power 6. That's the value of A. Any questions on that so far? Remember, this number here corresponds to the gradient of the line. Okay, so to work out the gradient, you need 2 points on the line. So you pick 2 points. You can pick any 2 points on the line. So guess what they've done in the book? They've picked the point 0.05 and 6.16, which is over here. And they've picked the point 0.77 and 5.68. Again, this 0.77, 6.8. I guess that's this point over here. Okay, and they've worked out the gradient. So they've done change in y over change in x. Okay, so to work out the gradient, the n is going to be the gradient. So n equals change in y, 5.68 minus 6.16 over 0.77, take away 0.05. That calculation will give you the gradient, which is negative, which is about minus 0.67. So that means I found the value of n and I found the value of a. So that means I can write down my equation. So remember, that was my model for the data, the original data. So I can now conclude that the population is equal to 1.6 times 10 to the power 6. That was my A, times r to the power of minus 0.67. Okay, so if you go back, so this is what the software predicted. So that website, I just entered the data into that website, my curve fit, and it predicted, gave me the equation by some other methods. So that's quite close to what we got. So you need to be able to do that kind of process with logs. So an equation of this form, where it's p equals ar to the n, okay, that will give you a graph of log p against log r. That's what you need to realize. Any questions? Okay, so that's one type of non-linear curve. There's one more type of non-linear curve, slightly different, but it's the same idea. Okay, this one. Okay, this is slightly different. Y equals a b to the x. So this time, x, the variable x is in the power. So before, x was not the power, x was the b term, but now x is now the power. Okay, so you can follow the same process to work out some kind of straight line equation. So you begin by saying, so again, this kind of graph is going to be some kind of curve. Okay, so you follow the same process. Log the left-hand side. Okay, when you log the right-hand side, this is a product. Using the rule for the product of two logs and the product of two terms, this can be written as log a plus log b to the x. That's from the first law of logarithms. Then using the third law, if you've got something to a power, that power can come down. So you get log y equals log a plus x log b. If you reorder it, write it in a different order. So basically, so log y is the dependent variable. Okay, the independent variable is just going to be x. There's no log involved. So you'd be plotting the graph of log y against x. Okay, and again, as before, this is just the y-intercept. The gradient though is log b. So remember, b is a constant. So the gradient of that line would be log b. So at the end of the day, what you end up plotting, the dependent variable is log y on the y-axis. The independent variable is x on the x-axis. So that doesn't change. So to work out the y-intercept, the value would be equal to log a. That would be the y-intercept. And the gradient would be log b. Okay. So the only difference between this example and the previous is that in the previous one, you would plot log y against log x. But for this kind of curve, it's log y against x. I'll do the example, this one small example. Okay, so this one is not too bad. They're giving you a graph population of bacteria. Okay, so P is the population of bacteria. The graph has gradient. Okay, so they've given you the graph of log P against T. T is in hours. The graph has gradient 0.6 and the y-intercept is 2. The scientist wants to model the bacteria population with this equation. Okay, so in other words, the P equals AB to the T is going to be some kind of curve. So it could be something bacteria increasing, bacteria decreasing, who knows? That's what you need to figure out. Okay, so you start off by write down the equation for the line. So the equation of the straight line, remember, is y equals mx plus c. But the variables, the y and x variables, are log p against t. So we know that log p is the y variable. Okay, the gradient is given to you, 0.6. The x variable is t. And the y-intercept is also given to you. It's just 2. So that is the equation of that straight line. So part B then, use your answer to A, find the values of A and B. So basically, you need to take it out of the logs. So remember, this log is log base 10. Okay, so when we talk about log, we're talking about log base 10. So you can think of it as log base 10 of P equals this. And that's your log equation. So take it out of the logs, the base is 10. So that tells you that 10 to the power of the right-hand side is equal to P. So just using the definition of a log to take it out of the logs. P is the base, so 10 to the power of all of that is equal to P. Is that okay? Any questions so far? Okay, I'll carry on. So you need to separate this out. So we can say P equals, you can separate it basically as 10 squared. Remember, you add the powers. So I can write it as 10 squared times 10 to the power of 0.6t. I can separate it because you add the powers to get 0.6t plus 2. So that tells you population is equal to 100 multiplied by, okay, you want it in the form P equals AB to the T. So we've got A is 100, looks like. So we can rewrite the second term, 10 to the power of 0.6 is a power to a power. 0.6t is 10 to the power of 0.6 to the power of t, like that. So we can evaluate 10 to the power of 0.6 on a calculator to get 100 times 10 to the power of 0.6 should be about 3.98. That is the equation for modeling the population of bacteria after T hours. So you can see that as the time increases, the population of bacteria is increasing. So it's increasing exponentially. Maybe like Corona, like that. And the very last part, interpret the value of the constant A equals 100. Okay, so this constant A equals 100, you need to interpret it. So you notice that when T equals 0, the population of bacteria is exactly 100. So in other words, the 100 represents the initial population of bacteria. So you could say constant, so A equals 100. 100 is the initial population of bacteria. And that's it for chapter 14.